We can also make use of the resistivity data, right, to understand what is known as longitudinal conductance. So, what is longitudinal conductance? Longitudinal conductance, right, suggested by these people, right, in their research article, Mohammed has suggested that longitudinal conductance is related to resistance, right. Obviously, longitudinal conductance is related to transverse resistance, which in turn is related to groundwater flow. Hope you can recollect, in the initial lectures I showed you there is an analogy between the way in which the current is flowing in the formation beneath the subsurface is related to the way in which groundwater can flow, isn't it? So, making use of this analogy, they have suggested a relationship between longitudinal conductance, which is equivalent to H divided by rho, where H is the thicknesses of the layer, right, and rho is the resistivity which we measure at the site, right. And using this relationship, we can determine what is known as transverse resistance. Transverse resistance R can be estimated using this relation, right. So, using this relation, we are able to determine the transverse resistance. What is the use of this transverse resistance? Because as you see in this diagram, transverse resistance is related to how groundwater is flowing in the formation. Hence, using the resistivity survey, right, electrical resistivity survey, we can estimate some critical aquifer parameters, right, because there is a similarity between groundwater flow and the current flow as brought out by these researchers, right. The transverse resistance T and the longitudinal conductance, yes, they are also known as Darcy-Roux parameters, because they are named after these researchers who have suggested this technique of estimation of transverse resistance as well as longitudinal conductance, right. So, they are inversely related, because longitudinal conductance is related to transverse resistance. Both are inversely related, as you see in this relationship, right. Then, making use of this, there is a way to estimate the transmissivity of the formation. So, what is transmissivity? Transmissivity is related to the Darcy's law, right. Darcy law for groundwater flow states that rate of flow of groundwater is related to the change in the head as well as the capacity of the formation to transmit water. Capacity of the formation to transmit water is known as hydraulic conductivity, referred by the letter K. So, transmissivity is the multiplication of K versus the thickness of the aquifer, right. Suppose if you consider this as a formation, right, where this is the water table below the surface, for unit width of water table, for unit width of cross section of the aquifer, how much of groundwater is getting transmitted, that is what is transmissivity. So, T is equal to K multiplied by the thickness of this aquifer, that is, this is B. Okay. So, there is a relationship between aquifers R, that means what is known as transverse resistance R is related to hydraulic conductivity using this relationship, right. So, transmissivity of the aquifer can also be estimated using the longitudinal conductance which we have measured, or transverse resistance. So, here aquifers hydraulic conductivity, or in other words transmissivity, is estimated using this relationship which states K multiplied by, which is K is the hydraulic conductivity multiplied by longitudinal conductance S, and here we have electrical conductivity. Electrical conductivity is a reciprocal of inversely related to electrical resistivity. So, electrical conductivity, if you can estimate making use of electrical conductivity meter, we are able to determine the transmissivity of the aquifer. So, this was given by Dr. Nivas and Professor Singhal from IIT Roorkee. So, they suggested this method of estimation of transmissivity from the electrical resistivity survey. And making things much more easier, a empirical formula has been brought out by Heigold in their study carried out during 1979, wherein they brought out a simple relationship relating the aquifer's resistivity with that of hydraulic conductivity, right. So, hydraulic conductivity and the resistivity of however, this is applicable to only granular aquifer. That means, aquifers which are having primary pores. Primary pores are the pores formed at the time of formation of the rock itself, right, a formation itself. Such granular aquifers, this relationship is applicable. However, it is an approximate estimate, right. So, using this relationship, we are able to determine the aquifer's hydraulic conductivity at different locations and different depths, making use of the resistivity which we have observed using the resistivity method. So, in the last two slides, we have understood there is a way to estimate aquifer parameters from the resistivity measurements. We had used these methods for the same site which we had seen, the South Chennai coastal aquifer, right, which we have been seeing. We could get the relationship between hydraulic conductivity and the formation factor. What is formation factor? Formation factor is the ratio of resistivity of the saturated formation to the resistivity of the water, that is the resistivity of the groundwater. So, formation factor F can be obtained using this relationship. How can we determine the resistivity of the formation? We have already got the resistivity of formation by conducting the electrical resistivity survey, right. Since we have conducted the electrical resistivity survey, we could get the values of the resistivity of the saturated formation at different depths below the surface, because we have the data of, as I told you, for example, when we do Schlumberger survey for depth sounding, we have this data of AB by 2 1 meter, apparent resistivity 2 meters. I am just writing as an example, right. You can also conduct at half a meter, 0.75 meter and so on, right. What is important here is, for different depths we have the corresponding apparent resistivity values. So, the apparent resistivity of the formation below the saturated zone. So, if you know we have touched the water table, let us say beyond AB by 2 5 meters, we may be in the saturated formation, that is this RF. How can we determine the resistivity of the water? We can take the sample of water and carry out the electrical conductivity, or as I told you previously, right, there can be a well existing in the region. There may be a well, this is the ground surface, this is the water table, right, this is ground surface. We may deploy a conductivity meter, right. We can arrive at the data of depth versus electrical conductivity, right, maybe 1 meter, 1.5, 1, 2 point, like that. So, at different depths we can measure the electrical conductivity. So, here we have depth versus electrical conductivity, here we have depth versus apparent resistivity. So, for different depths we have RF as well as RW. We can get the formation factor at different depths. So, in this study we had related formation factor with the hydraulic conductivity. So, here at this side, actually hydraulic conductivity can also be estimated by pumping test, right. In pumping test, what we do is, this is the ground surface, we pump a well, response of the pumping is measured in some nearby observation wells. This is the pumping well. So, this is the water table before pumping. When you pump the well, a cone of depression gets formed due to this. There is a drop in the water level. So, with respect to time, we observe the drop in the water level using the groundwater flow equation or which are based on the Darcy law, we can estimate the hydraulic conductivity. So, this is how for this site hydraulic conductivity has been estimated at different locations, at around 10 locations by pumping test. So, hydraulic conductivity estimated by pumping test, we compared it with the formation factor derived from resistivity survey. This is by resistivity method, and hydraulic conductivity was obtained by pumping test. Right. There is a reasonable comparison, right, between the formation factor and the hydraulic conductivity. Then we continued further, we compared the hydraulic conductivity of the formation with the hydraulic, or in other words, I do not want to use the word hydraulic, I will say compared with the aquifer resistivity. That means modified is inversion. By inversion, we obtain the aquifer resistivity. So, here is a comparison of field measured hydraulic conductivity with the aquifer resistivity. There is a reasonable relation. Then we compared the transmissivity, field derived field transmissivity was compared with the transverse resistance. How did we obtain transverse resistance? Using this relationship, right. So, using this relationship, we obtained transverse resistance that was compared with the field measured transmissivity. So, as you can see here, there is a reasonable comparison, there is a linear relation. However, we cannot expect such a nice relationship everywhere, since this site, as I told you previously, right here too, all this relationship between the analogy between groundwater flow and the current flow is reasonably clear only in the case of more or less homogeneous granular aquifers. Fortunately, in this case, I told you, as I told you before, this is the ground surface, beneath that we have only medium to fine sand everywhere. Below the sand, we have rock. This aquifer is more or less, I cannot say homogeneous, but reasonably throughout 30 to 40 meters. The thickness varies, right, vary from 15 to 70 meters in this area. So, if you consider only the top sandy layer, for which this relationship works well, right. This was a study by these two people who are currently working with Dr. Senthil Kumar and Dr. Gnanasundar. Both of them are working with the Central Groundwater Board. So, this study we could clearly bring out a relationship between electrical resistivity and the pumping test derived aquifer parameters, especially hydraulic conductivity and the transmissivity, right. Then we did another study to understand the subsurface geology. This study was carried out in the state of Telangana in a region called Sripalli, wherein we did vertical electrical sounding at different locations. Why did we carry out this study? Mainly to understand the subsurface geology, right. In order to understand the subsurface configuration, we conducted electrical resistivity sounding at different locations, right. Then making use of the measurements made at different vertical lines, we have prepared what is known as a resistivity fence diagram, right. Electrical resistivity fence diagram, here red ones, and here you can see this is the resistivity variation, right. The red ones are having low resistivity. So, that means this is the top, this is the ground surface, right. As the depth increases below the ground, resistivity values are also increasing. Using this, we try to decipher the zones which are having soil, that is upper regolith, completely weathered material, then moderately weathered hard, then highly weathered rock, moderately weathered rock, beneath that we have the fractured rock. So, we were able to understand the thicknesses of different layers below this particular area, right. Then making use of the survey we conducted at different locations over this profile, right, we could derive the three-dimensional resistivity, subsurface resistivity diagram, right. Using some standard interpolation software, we have created the subsurface image. As you see here, right, the topmost, the red part is having completely weathered soil, right. That means weathered rock turned into soil where the resistivity is very low. Little bit beneath that, resistivity is slowly increasing, right. Somewhere at the bottom, resistivity goes up to nearly 1500 to 1700, right. So, indicating right at the bottom we have the reasonably fresh or fractured granite. Here we have soil, then weathered rock maybe up to this depth, then followed by that we have the comparatively fresh granitic rock. We could, when we do such a investigation, we need to also field verify whether our interpretation is reasonably correct. Then we measured the depth to the water table in a existing large diameter well. Here you can see upper few meters are completely weathered, then we have moderately weathered rock, then we have water table. So, we could compare this with the interpretation we have derived from the resistivity data. Then we have arrived at the thicknesses of layers beneath the survey, beneath this study site at different locations. This is another application wherein this was also a study carried out by one of our PhD student Murugan, right. So, in this study we were able to understand the subsurface characterization. We are able to characterize the subsurface by resistivity survey coupled with some field observations, right. Here is another study wherein we wanted to study the effect of tidal fluctuation on a coastal aquifer, right. This is a coastal aquifer, this is the sea level. The sea level varies nearly by 1 to 1.5 meters, right, due to tidal fluctuations, right. So, these are all the times having high and low tide close to Chennai, right. We wanted to see the tidal fluctuations on the groundwater table, adjacent groundwater table. So, we conducted resistivity tomographic survey at a site at different times, right. This is the tidal level fluctuation. This was also quite old study conducted by one of our postgraduate student, right. So, here is the variation, right. Though the results are not come out very well, what I wanted to emphasize here is we are conducting the study at the same site, but we are repeating the survey every 3-4 hours. We were there at the site, that means the student was there at the site, carried out the survey nearly for 2 days, right, carrying out the survey for different high tides, right. This is all are high tide, in between we have low tide. So, what is evident from this image is completely the resistivity tomogram changes, right. I do not want you to interpret, right. There are a lot of question mark here, right. We did not completely process the data, but what is clear is at the same site at shorter time intervals, right. We started from 1st March, the study was conducted up to 2nd March, right. Nearly for 1.5 days, 2 days, measurements were taken at different times, maybe every 4 or 5 hours. Beneath the surface, the resistivity varies. So, this is time domain resistivity survey. That means, that is the 4th dimension of time also we have taken into account. A study carried out by one of my collaborator from the Water Research Institute, Bari. wherein they are making use of electrical resistivity survey to understand the effect of recharge from a small percolation pond. So, here is a percolation pond, right, of about 2 meters by 2 meter, right, wherein resistivity survey was carried out, right, at different times. Just before filling up the percolation pond, a resistivity profile beneath the surface was obtained. Then after some time gap. So, this was filled after 80 minutes, the survey was repeated. So, here again it is a time domain resistivity survey. Previously resistivity was comparatively higher due to the infiltration, right, resistivity has decreased, right. In other words, we are able to understand the migration of groundwater into the earth. So, when we repeat this survey at different times, we will be able to quantify the impact of this infiltration pond into the earth. So, here are some examples we have seen, real life examples carried out. Most of the studies were carried out by others. I have also made use of some of my collaborators' work here to highlight you the applications of the resistivity methods. Obviously, all methods, in any investigation method has got some limitations. Some of the limitations are interpretation may be ambiguous, right. Each one of us can interpret the data in different way. So, how can we correct ourselves? As I was explaining to you, always it is preferable to compare with the field verified data, maybe a open hole well as I had shown you in the picture, or a borehole log collected during drilling. We need to compare and cross verify our interpretation. And interpretation is applicable for simple conditions. For example, in coastal aquifer we have only sand everywhere. So, interpretation is reasonably easier. The complications there is only due to change in the quality of groundwater. In very complex area, interpretation is little bit difficult. And I didn't tell you more about the topographic effects, right. Suppose if you have a sand dune, we had some sand dunes also, right. The elevation of sand dune, let us say 4 meters, when we plant the electrodes like this, the elevation difference also will result into some error in our readings. So, we need to overcome these issues, right. When we conduct a survey in a mountain slope, preferable to do a profile perpendicular to the mountain slope, so that all electrodes are kept more or less at the same elevation. So, this will also have a topographic variations, will have an impact on our investigation, right. And depth of investigation is usually limited. Why? You know the reason already. Depth of investigation is related to the distance between the electrodes. Many a time there will be some logistic constraints. There will be logistic constraints in the field, because you need to investigate 200 meters below the surface. If you are using Schlumberger method, the electrodes have to be kept at 400 meters. So, you may not have a clear accessible region, right. These are all some limitations. So, sometimes we need to water the electrodes. When we conduct survey in the beach, resistivity of the upper layer is very high. So, current won't be able to pass. So, we may need to add some water at the site. So, everywhere we add some water at all the 4 electrodes to make current to pass through, or we may need to use long electrode. When we conducted survey in the coastal area, we used nearly 1.5 meter long electrodes. The entire 1 meter will be hammered into the earth, so that the current can easily flow into the earth. So, these are all other limitations. And depth determination is, the accuracy of depth determination is little bit lower, right, compared to other geophysical methods. In seismic methods, determination of depth is much more accurate, whereas in electrical resistivity method, determination of depth of different subsurface layer is only approximately. So, we need to compare and correct ourselves with the borehole log which we would have obtained by drilling methods, right, and also sensitive to minor variations in the subsurface, right, especially beneath one electrode we may have some clay zone or we may have a boulder buried. All these things will lead to some noise and error in the interpretation. So, in this lecture what we had seen is, we have seen what is electrical resistivity methods specific applications, right. First we had seen how contaminant plume is migrating below the surface of the earth. We could understand the migration by repeatedly measuring the electrical resistivity survey. Then we had looked into seawater intrusion, how seawater intrusion was deciphered using electrical resistivity tomogram. Then we also had seen, we had seen with the tomogram, then we had also seen how we can prepare a 3D image to illustrate, to understand seawater intrusion. Then we had also seen how vertical electrical sounding carried out nearly at 70 locations can be converted into a 3D data set to understand the spatial variation in apparent resistivity and the depth wise variation in apparent resistivity, as well as profile wise variation in apparent resistivity we have understood from here. Then how we can understand the subsurface geology by resistivity survey. I showed you an example from Telangana region wherein we conducted several vertical electrical soundings. Toward the end we had seen this slide, how infiltration from percolation pond can be studied by resistivity images, right. So, these are all some site specific applications. I am sure you would have got a reasonable understanding of basics of electrical resistivity method and how the resistivity method is carried out in the field, and what are all some of the site specific applications you would have understood based on the case studies which I have presented to you today. Thank you very much. We will meet during the next lecture. Have a good day.